suppose that we have a particular medication which during medical trials resulted in clinical trials resulted in a certain side effect for 6% of the patients in the study. Now, before we get into the three different parts, let's take a look at why this fits the scenario of if we count how many experience the side effect, that we have a binomial distribution of that count. So first of all, if you saw the parts that were further down, we were looking at 100 that are prescribed that particular medication. And so there's a fixed number of observations or trials there. We're going to call that little n. Trials are independent of each other. So what happens with one in a sample is not going to affect what happens in another, whether they experience the certain side effect or not. Part of that is perhaps due to the fact that the sample was obtained randomly. Maybe it was a simple random sample. Two outcomes. The outcomes here are that the patient experiences that certain side effect or they don't. Now, calling them success and failure to me sounds a little strange. Our concentration is going to be on whether that side effect is experienced. And so success is merely what we're concentrating on. Finally, the probability is going to stay the same in all trials. That'll be little p. We had 6%, which as a decimal, we would have that p is 0.06. So with that stated, let's take a look at the three different parts. So again, n is 100. And let's see here, we're supposed to compute the mean and standard deviation. Now, we could, using a formula I'm going to show in the last part, we could do what we did for discrete random variables in general. Multiply a score by the probability of that score, do that, add up all of the products we would get after doing that for each score. But we could have as little as capital X equaling 0 or 1 or 2 or 3 on up to 99 and 100. That would be 101 probabilities we would have to find out. Sorry, yes. 101 probabilities we would have to find out. And then adding, that would be 100 additions to do. It has been found instead that we can, for a binomial random variable, find the mean by multiplying n times p, and then find the standard deviation with taking that n times p that we would find out with the mean times 1 minus p, which, by the way, would be the probability of failure. 1 minus little p would be the probability of failure. Multiply n times p times the quantity 1 minus p, and then take the square root at the end. We're going to round to the nearest hundredth on these. Okay, so 100 times 0.06 is 6. And the standard deviation, we just found out that n times p was 6. 1 minus 0.06 would be 0.94. Multiplying the 6 and the 0.94, and then taking the square root, finally rounding to the nearest hundredth. The mean, that wasn't necessary to do any rounding because it terminated as a whole number. Now, what does the mean tell us? By the way, that could have been typed in all at once. Let me show you that real quick. With proper use of parentheses there, we could type in square roots of 100 times 0.06 times 1 minus 0.06. And again, we're getting 2.37 when we round to the nearest hundredth. Okay. So interpret the mean. Remember that we should be thinking about what's happening in the long run. What if we were to get simple random samples of 100 patients, prescribe the particular medication, do that over and over? What if we could get all simple random samples of size 100 from people that have been prescribed that particular medication? For every 100 patients prescribed the particular medication, the mean 6 is going to be the number of them that would be expected to experience the certain side effect. That's not that we would actually have 6 in every group of 100. But if we had all simple random samples of size 100 from people prescribed the medication, then we could have the mean from all those different simple random samples being 6. And finally, would it be unusual if 10 of the patients prescribed the particular medication experienced a certain side effects? And as I've stated before, this can slide around a little bit. What do we call an unusual event? For right now, we're going with an unusual event is an event with a probability below 5%. I forget if we allow exactly equal 5%, so that we have to have less than or equal to versus less than. I don't remember that right off the bat, but that's not going to matter in this case, number one. Number two, sometimes they'll actually be a little more generous and go with 10%, other times 1%. So calculating the probabilities, since it is binomial, here's our formula. And I stated that n was 100, r would be 10, and that shows up in the combination. It shows up in this exponent. And I'm going to show this calculation also on the TI-84. So we had 100 C10 times 0.06 to the 10th. Scroll it to the right before you type the next base. Now we already know 1 minus 0.6 is 0.94, but you could have typed it as I did previously. And we also know that 100 minus 10 is 90. So the same result of 0.0399 when we round to 4 places. I didn't show the rounding here because we were just asked, is it an unusual event? Well, that is less than 0.05 or 5%. So yes, it is an unusual event. And we would not know that without doing the work. With the mean being 6, with the expected value being 6, 10 might not seem like it's all that far away from 6. And yet, with the work we've done here, well, relatively speaking, apparently it is far enough away. And so that is an unusual event.